So let's take a look at three of the homework assignments for mysteries of the first and second derivative, and this is really to reinforce the all about me sheet information into your brains. And so what you'll see in these three problems, we have three different scenarios. In the first one, we're given a graph of the first derivative. In the second problem, we are given an actual piecewise function. And in the third problem, we're given a table of values. So let's jump in here. In number one, we are given the graph of a first derivative, which we can see right here, and they emphasize the fact that this is the graph of the first derivative right here. So make sure the first thing that you do is establish in your brain that you are looking at the graph of the first derivative, not the original function, not the second derivative. The graph above shows the graph of f prime, the derivative of a function f. The domain of the function f is the set of all numbers on the closed interval from -3 to 3. So whatever we're discussing, whatever we're responding to in this problem, it's on the closed interval from -3 to 3. Letter A. Change colors here. For what values on the open interval from -3 to 3 does f, original function, have a relative or local maximum, relative or local minimum? So what we're looking for on the first derivative, and if you have your All About Me sheet, hopefully you know this, but what we're looking for a local or a relative maximum is where the first derivative is 0 and changes from positive to negative. So on my graph up here, I'm going to color the places where the first derivative is 0. So the first derivative is 0 at -2, at 0, and at 2. However, at x equal to 2, the sign of the first derivative does not change. So 2 is a critical number, but no local max nor local min will occur there because the sign of the first derivative doesn't change. Now back at x equal to -2, we can see that the first derivative changes from positive to negative. And so if the first derivative changes from positive to negative, at a critical number we have a relative maximum. And you'll see the write-ups on the next page, but I'm just going to walk through and help you to understand the thinking on this particular page. At x equal to 0, you can see that prior to x equal to 0, the first derivative is negative, and after x equal to 0, the first derivative is positive. So if the first derivative changes from negative to positive at a critical number, you have found a local minimum on the original function. All right, so let's take a look at expectation. We've talked about writing. Writing is really important. So we're talking about f has a local, and you can use relative. I think they use the word relative minimum at, here's the x value, here's the y value. Make sure, one of the things that many of my students forget to do is establish that you have a critical number. So tell me that the first derivative is 0 at the critical number, and then tell me the first derivative of the function, not the number, changes from negative to positive. And then the same thing for the local maximum. Here's the x value, the y value, establishing the critical number, telling me the first derivative function changes from positive to negative. So this is B for my class. This is the minimum amount that you may write to get credit. Also notice that the person who did this work took the information off of the graph, and they converted the graph basically into a number line. For some students, it's easier to read the number line than it is to read the graph. All right, let's go back for letter B. I'm going to clear these annotations. So in letter B, we are looking for values of x where the graph of f original is concave up. So we have to think about, if you look at the All About Me sheet, look in the first derivative section. So here you look in that first section and you're looking for concavity. So what you will see is that to determine concavity using the first derivative, you need a graph. Well, good news, guess what? Over here to my left, or to the left of this writing, there is a graph. So first derivative concavity, where the first derivative increases, the original function is going to be concave up. Where the first derivative decreases, the original function will be concave down. So we can see that, let's see, we're looking for concave up, so we're looking for increasing. So we can see the graph of the first derivative increases on this blue interval and increases on this blue interval. So we're talking from -1 to 1 and from 2 to 3. Reason being, and you justify with first derivative. So let's take a look at the write-up. Write-ups are really important. The original function f is concave up on the intervals that I stated because I'm using the first derivative is increasing. And then finally, let's go back to letter C, restart, clear those annotations. For letter C, we are using the information that we have to sketch a graph of a possible original function. Now let's go back, let's look. Now this is what I call an anchor point. That just anchors so that for a reader to grade the work, it's an anchor point, it keeps the graphs in the same vicinity. So what we're looking for when we sketch a possible graph is shape and properties. And if you include all the properties, when I say properties, I'm talking about the proper increasing, decreasing intervals, the proper concave intervals, the local maxes and mins occurring where they are supposed to occur. Now, how high you go for a max, how low you go for a min, not really graded that much. That's where that whole shape idea comes from. So when I sketch a graph, and I'm going to pull this down and let you see, I would start with the anchor point, which was -3, 0. So that point clearly is going to be the first thing that I put on my graph. And you can see that a number line was created for the second derivative right here so that they could see the concavity. All right, so I'm going to go back. I have my local maximum earlier at x equal to -2, so I have to make sure that when I sketch my graph that I get a local max there. From my number line, let's see if I can grab that and bring it down. It may be locked in. Yeah, it's locked in. I can't bring that. Here, I'll do this. Give me 1 second here. Tools, camera, area. Now, I don't love these number lines that they have on here because they have more values than the critical numbers on the number line. Don't like that. It gets a little bit confusing. What they're really showing you is that they're checking multiple values. All right, so let's do that, and all right, so there's the first derivative number line, and then the second derivative number line. So what you can do here to sketch that graph is do your arrows. There's your decrease from -3. Oh, sorry, that would be an increase, would it not? Come on, Jernigan. All right, so increasing, decreasing, and then increasing. And then for concavity, we're looking concave down, concave up, concave down, concave up. I will tell you sometimes the concavity is one of the hardest things to do, and that's where you're going to use your eraser quite a bit. So for example, when concavity, like right here, changes from down to up, like right in here, concave down to concave up, think of like a cubic graph. So it flattens, and then the point of inflection would be like right there where the concavity changes. So you kind of have to practice with that and keep adjusting. Another tip on sketching the graph of the original function is to, when you make your x and y axis, don't bunch your tick marks together like that. If you bunch your tick marks up, you've really limited yourself. You're going to have to make a lot of things happen in a very, very, very small space. All right, so let's come back down here. We put on the anchor point for sure. Now, one of the things you could do before you do the graph is, like, you know there's a local max at x equal to -2, so you could just randomly stick a point up here and go, well, I'm going to put a point there to remind me that that's a local max, and maybe right here a local min, and then you can start adjusting. So right here you can see that they have a concavity change at -1, which is indicated up here on the second derivative graph. So I'm following the first derivative number line, which says I'm supposed to increase until I get to a maximum at x equal to -2, so that takes care of that. I'm supposed to be concave down, so I have to be cognizant and aware that the concavity is down. And then I have to try to make it look like the concavity is switching. So I'm concave down here, and then I have to switch to concave up, which is happening right here at x equal to -1. I'm reading the number line, then the first derivative number line says I'm to decrease until I get to 0, so I'm going to decrease and stay concave up. Then after 0, I'm going to increase for the rest of the graph. I'm concave up. Then I look at the next value. Concavity is changing at x equal to 1. So there's that little cubic thing that I was telling you about. It's happening right here at x equal to 1. So I go to concave down in that region. And then again, the concavity changes, and there's like that little cubic action right here at x equal to 2, and the graph continues to increase. So when you're sketching the graph, you're not going to just start at -3 and just sketch the thing out. You're going to be doing some erasing and changing and adjusting and fixing, and it does take practice. All right, let's go on to number 2. In problem number 2, we have a piecewise function as given here. This is the original function. It is a mysterious function because we do not know the values of k and p. Something important to understand about k and p is that k and p are numbers. They are not variables, meaning that you treat them as numbers. You do not treat them as variables. So for letter A, we're looking for the value of k and the value of p that will force the original function to be continuous and have a first derivative. So the word differentiable in this case is a hint that you need to take the first derivative. So I have 2 clues that are going to help me find the value of p and the value of k. And if I don't use both of those clues, I won't find them. All right, so the first piece I'm going to deal with is continuity. So I'm going to turn the page and debrief that for you. So for continuity, we know from our past that we're going to take this, what I call a breaking value, and substitute 1 in place of x, and substitute 1 in place of x in each of the functions. So in the first piece, I get an output, a y value of 1, and in the second piece, I get a y value of 1 plus k plus p. For continuity, these 2 y values must equal each other, so that's what I'm doing right here, setting the 2 y values equal to each other. And the only thing I can figure out there is I can subtract 1 from both sides and find out that k plus p is equal to 0. I can subtract p on the other side to find out that k and p are opposites of each other. But I do not figure out what the value of k or p is yet because, as I said, there is a second piece. Differentiable says take the derivative. When you take the derivative of a piecewise function, you take it in pieces, meaning you take the derivative of this first piece using simple power rule, so you get 2 minus 2x. You take the derivative of the second piece. The derivative of x squared is 2x. Now remember what I said about k. It's a number, it's a coefficient. The derivative of kx is k, and the derivative of p, which is a constant, is 0. Then we're going to do the same thing we did for continuity. We're going to substitute in the 1, and we're going to substitute in the 1, and so we output these 2 first derivative values that need to equal each other. So this is me setting the two values equal, and yay, that allows me to find the value of k to be -2, which allows me to come back over here and find the value of p, let me slide this down, to be +2. So I have my 2 values of k and p. Now that will allow me to go back and rewrite my original function. So here's original f of x equal to, let me bring that down so I can see it. So 2x minus x squared for the first piece, and now I'm going to substitute k, which is negative 2, and p, which is positive 2, and that's going to be on the same interval. Now, the reason I wrote that down so I could see that original function, because for part B I am looking for increasing intervals. So I'm going to need the first derivative. So the first derivative of the first piece is 2 minus 2x that we already know about. For the original function, I'm taking the derivative now that I've substituted k and p, and I get 2x minus 2 for the derivative of the second piece. My critical number is going to be 1, and I can verify that by setting each piece of the piecewise equal to 0, and in both cases I get a critical number of 1. When I do a test value on the left of 1, such as testing the value of 0, that 0 goes in here because it is less than 1. When I choose a test value of, for example, 2, it goes into the second piece because 2 is greater than 1. And what I can see is that the function increases everywhere. For whatever reason, I don't think I have that answer written down. I don't know why. So the answer is f of x increases. You can either write it from negative infinity to infinity, or you could write it from negative infinity to 1 and 1 to infinity and get credit because f prime of x is greater than 0. Lastly, for this problem, we're looking for intervals of concavity, or no, actually we're looking for a point of inflection. So we're going to need to find the second derivative in pieces again. The second derivative of 2 minus 2x is negative 2. The derivative of 2x minus 2 is 2. And so I get concave down, concave up. So since the sign of the second derivative is changing, there is a point of inflection at x equal to 1. And that's my breaking value. So that's problem number 2. All right, for problem number 3, let f original be a function that is even. That is the most important word of the given information because an even function, as you will recall, means that you have a graph that is symmetric about the y-axis. So I'm going to draw a graph that symmetric is pretty good. That means it reflects or folds over the y-axis. All right, the next thing that I notice is that whatever information I provide is on the closed interval from negative 3 to 3, and the function has properties given in the table below. So I notice that they're giving me information at 0, from 0 to 1, at 1, 1 to 2, at 2, and 2 to 3. In other words, if I were to think about a number line over here, they are actually, let's redo that number line because we're only going from negative 3 to 3, so let's block that off. Okay, so if I were to create a number line, it would start at negative 3 and it would stop at 3, and I'll put 0 in the middle there. So in this table of values right here, they are only giving me, or at least outright, the information from 0 to 3. Well, that's where this whole even function information comes into play. Because by giving me the information from 0 to 3, they're actually also giving me the information from negative 3 to 0 because I have to understand this idea of an even function. So let's think about that for just a minute. In this table of values, this is the original function, this is the first derivative, this is the second derivative. So let's look at our sample even function to figure out how the function behaves on either side of the origin, because we're reflecting. I'll put a little dot, or actually I'll just dot my y-axis. Okay, and of course that's where x is equal to 0. So if I choose a sample value of x, so for example I'm going to choose this value of x, and then over here on the right hand side this would be the reflection of that point. Notice at opposite values of x, the y values are the same. So that's really important for me to understand, because when I go in here to the table and I see that, for example, at x equal to 1, the y value is 0, that also tells me at negative 1, the y value is also 0, because the opposite x values have the same y values. Okay, now let's think about first derivative. First derivative. On this side of the graph, or at this point, the graph of the original function is decreasing, so the first derivative would be negative. But over here, the graph of the first derivative, the graph of the original is increasing, so the first derivative would be positive. So in this case, the signs would be opposite on either side of the origin. So for example, where the first derivative is negative from 0 to 1, that means from negative 1 to 0, the first derivative would be positive. So what I'm trying to say is we're going to create a number line, but we're going to create it on both sides of 0, not just on the right side. Lastly, let's look at the concavity. So over here on the left side of the origin, the graph is concave up, and in the same region on the right side, the graph is concave up. So that tells me the second derivative will have same signs at the symmetrical intervals. Now let's see if they do the number lines on the other side. Yes, they do. Okay, so here's what I'm talking about right here. So here's the information that they gave me from 0 to 3, and from 0 to 1 they gave me first derivative to be negative. So when I go to the other side, to the symmetrical interval, the first derivative is positive. So where I have negative, 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 positive, I'm going to reflect to be positive, positive, negative, because the first derivative have opposite signs. All right, let me clear these annotations. Now what that tells me about the original function is that I'm going to decrease, increase, increase, decrease, decrease, increase. Make sure you put your arrows and make sure you name your number line. For the second derivative, let's come down here, number line. Remember what we said, the second derivative has the same sign, so these are symmetrical intervals, symmetrical intervals, symmetrical intervals, and so the second derivative had the same sign, so the concavity is the same. So that would tell me that we are concave down, concave up, up, down, down. Make sure you put your concavity arrows because you're going to need to graph and name your number line. So for letter A, they are asking us find x coordinate of each point for which f attains an absolute maximum. Now remember, there is only one absolute maximum, highest y value, but it could happen, it could occur more than once. You could hit that highest y value more than once, or the absolute minimum similarly. So when we look at the number line, we can see that now remember this, the function is even, meaning the graph will be symmetrical. In fact, it might be easier to create the graph to see this. So I'm going to pull this down. I'm going to cheat, not cheating, but part C is to actually make the graph, and that will kind of support what's happening here. So by the intervals of increasing and decreasing, you can see that the highest y value, because we have one interval of decrease, two intervals of increase, and then two symmetrical intervals of decrease, one symmetrical interval of increase, so to speak. So the highest y value, that double increase, would have to take me to the highest y value at x equal to 0. And that means that the absolute minimums would occur at, even though that's a local minimum and a local minimum, since we don't go any lower than that on the graph, those would also have to be the absolute minimums. This one I don't think asked for a justification. It did not. Reason being, it's a hard justification to write up. So in this case, you are only answering what they tell you to answer, which is to provide the values of x where the absolute maxes and mins occur. For letter B, we are looking for points of inflection, and so that's why I created my second derivative number line, and I'm looking for where the second derivative changes sign, which occurs at x equal to -1 and 1. Did they ask for justification? Yes, they did. Shame on me, I don't have a justification. That would be, well, this is not my work, because the second derivative changes signs at these values. So I'll give myself a -1 for not writing my justification, maybe -2. Now creating the graph, this one's a fun one. This is like the Hershey Kiss graph. The concavity gets funky here, and you have to be concave down and decreasing. So concave down and decreasing can look like that, but then you have to go concave up while increasing. So that's what creates our little bird function, and that's what's happening here. So we have a graph that's continuous, but if you look back, it tells us that the derivative is not defined at x equal to 1, so that means we're going to have, well, the graph is continuous, so the only thing that we can have is either a cusp or a sharp term. We can't have a discontinuity, and that happens again at x equal to -1. So there's a lot of things, a lot of aspects that have to be built into this graph. And so you follow your number line, you use your eraser. Did they give us an anchor point here? I think they did give us some, yeah, they did. They told us the x value at 0 is 1, 0, -1. So they told us this x and y value, I already forgot where the other ones were, but you can see on the other side. So you would plot those points first. So those are the first 3 problems for the mysteries. Hope it helps.